All right, so now we're going to cover the full v of t, basically the full sinusoidal function, and we're going to cover all three parameters that make it up. Okay, so we've got the sine function, which we've talked about, kind of beat a dead horse there a little bit. We obviously have dependency on time. We're looking at time domain for all of these things. And then we have the three major the three major parameters that we can change to alter our sine wave, okay? The first one is Vm, which is the amplitude. So I'm going to, underline that in blue. The second one is going to be the frequency, which is kind of wrapped into this omega term, which we've seen. Again, let's remember that omega is equal to 2 pi times f. And they are, obviously proportional. The frequency is just omega, or the angular frequency is just the frequency in hertz multiplied by 2 pi to get it into radians, right? And then the last thing here is phase, which is one of the only things that we haven't talked about quite yet. Okay, so what we're looking at when we look at amplitude is we are looking at the height that our sine wave reaches. Okay, so if we look over here, this first sine wave, let's just call it V1 of t. It has an amplitude Vm1, let's just say. And we know that it goes up to Vm1 and down to minus Vm1, right? We can see that. Okay, let's call this second one. Let me go to a darker blue. We'll call it V2 of t. And this one has a different amplitude. We can see visibly that the amplitude of the second sine wave is larger than the first sine wave. So I'll call this Vm2, and we'll call this minus Vm2. And then I hope you agree with me if I say that Vm2 is greater than Vm1, okay? So hopefully that's pretty straightforward. That is what the amplitude does. This term out in front of the sine function just scales the height of the maximum height of my sine wave, okay? That's the amplitude. The frequency, basically, as we've talked about time and time again now, tells me how many cycles per second I'm looking at, or all inversely tells me how long one cycle takes. If I take the frequency and solve for the period, or vice versa, I can say that my period is equal to 1 over my frequency. And again, my period tells me the time it takes to complete a single cycle. Okay, so for this top sine wave, let's call it V1 of t again, or I guess I can call it V3 of t now. Let's call it V1. Sorry, let me just be consistent since all the signals on the top are the same across the board. Let's just call that V1 of t, and then we'll call the bottom one V3 of t or something. I hope you'll agree if I say that this function, this V1 of t, has a frequency f1, and I hope that you will agree if I switch here to V2 of t, and I say this is my new period, much shorter period. Since this is a much shorter period and it's in the denominator, we know that our frequency is much longer, which you could definitely see that, the way I actually wrote it out was it would be twice as long. So, or sorry, half as long for a period, twice as fast. So the frequency f2 is greater than f1. And that means that, let me call that t1, and we can call this one t2. And then I'll also write that t2 is smaller than t1, okay? Hopefully that makes sense. You can see that the second sine wave is faster. It has more cycles per second. And as a result, it has a smaller period, which is the time it takes to complete a single cycle, okay? So I think I've said enough there. Last thing here is the phase. Okay, so you can see, maybe you don't immediately recognize the difference between these two, but let me call this again V1 of t, and then I will call this bottom one, let's go to green, I'll just call this V2 of t. Well, hopefully, if you don't notice, I'm going to point out what the phase is. The phase is how far along is my sine wave shifted in time. So you can see right here that the midpoint, or the zero crossing, occurs at the origin. That zero crossing in the sine wave below actually occurs later in time, right? Well, if I think about it in terms of time t, then I could write this as a time delay, which we would label TD. But I can also write this as a phase shift if I'm thinking in terms of angles. So like if I'm saying that this is a cycle, like I was on my circle, I could call this 2 pi. I could call this 3 pi over 2. I could call this pi, and I could call this pi over 2. And then this point right here, this would be at some angle that is greater than 0 but less than pi over 2, right? That would be my value for phi, which I have written right here, right? That's my angle phi. I can write it in degrees or I can write it in radians. Exactly the same way that I would write that this term would end up in either degrees or radians. Again, to stay consistent and to enable us to use this sine function, I need to write my angle, my phase angle, in terms of degrees or radians, right? And so all the phase is telling us, again, the phase angle is telling us how far along is my sine wave shifted. Because when we have circuits that have different impedances, different elements, the sine waves that we're working with will scale, they'll change amplitude, and they will shift in time, which is equivalent to a phase shift. And so when we're solving circuits in the AC, kind of the AC realm here, we're going to see that instead of going from one DC voltage to another like we did in 220, we're going to go from one amplitude to another and one phase to another as we move throughout the circuit. So we need to keep track of our phase, okay? So this sine wave up here could be our reference sine wave. That might be our source, which would have a phase angle of 0, and I would just write this as Vm sine of omega t, and I could write plus 0 here, but there's really no reason to. That one has no phase shift. My V1 of t, and then my V2 of t, which I have down here in green, would be a Vm sine of omega t plus some phase angle, which I have written right here. Okay, so that is the explanation of the sine wave parameters. Hopefully they make sense. We've got our amplitude, our frequency, and our phase. And this right here is the expression we are going to see as the standard for basically all the signals that we're looking at when we're looking at signals in the time domain. I actually don't know what I'm talking about in the next video, but I'm going to go ahead and end this video. So let's just stop that right here.